I know you guys are all very sad that the computer worked, but here we are. We're getting started. We're jumping into the next chapter here. This chapter is on solutions. When something is mixed with something else and there's not a chemical reaction, they just like to hang out together, right? So that's what we're talking about today. And this is chapter 12. I'll give you a moment to write that down before I start again. Solutions. Solutions are any time when one substance dissolves another substance. So quick examples would be not or tall. There you go. Quick examples would be tap water. Tap water is mostly water, but there are other things in the water that the city puts in there or the county puts in there to keep bacteria from growing or keep algae from growing or things of that nature. So it's mostly water, but it's got some other stuff in it. Ocean water would be another example of a solution. It's water, but it has more stuff in it than tap water does. It's got salts, and it has some dissolved organic matter, and it has various minerals of all kinds in there. So and dissolved gases also. It's a solution as well. Any solution is where you have mostly one thing and a little bit of something else, and the little bit of something else is dissolved in the mostly one thing. Okay. The fancy words for this, the scientific jargon for this, is that it's variable composition in one phase. In other words, if you were to sample this thing, this solution, you would find that it's not all one substance. It's not a uniform, pure substance. It's variable composition. There's different things in there. In one phase means when you look at it, it looks like one thing. You don't look at tap water, well, hopefully you don't, look at tap water and see chunks, right? Then that wouldn't be a solution, then that would be a suspension. But a solution is something where you only see one thing. It looks like one thing. So we'll give you lots of examples, but a single phase means to the naked eye, without scientific instrumentation being involved, it looks like one thing. But if you were to look at it more carefully, there is in fact more than one thing in there, okay? Variable composition of one phase. It's homogeneous. It's uniform. It's blended together, okay? You don't see pieces. Majority component we call the solvent, the thing that does the dissolving. We call a solvent. And there is more solvent than solute. Solute is the thing that is dissolved. So in tap water, H2O, water is the solvent. And a little bit of chlorine and a little bit of minerals for flavor is put in there, and that helps the water be what the county wants it to be, and that's the solute. Those would be the solutes. There's also probably some dissolved gas in there as well. So solute, solvent, solution. These are all words that you should have. And just pictures again. A solvent is the majority component that does the dissolving. The solute is the minority component that is dissolved. Okay? And we talk about it being in one phase and being uniform. So this, I don't know what this is. This is broth maybe of some kind, or Jell-O getting ready to be made. But let's call it Jell-O. The Jell-O powder, the solute, has been dissolved in hot water, the solvent, and it all looks uniform. It's one thing. It's in one phase. Here, this is oil and water, and you will see that this might be oil and soda because that water is kind of brown. But anyway, this is two substances, and they are not one thing. This is two phases. Here you have the one thing and the other thing, and then there's a boundary layer where the two things are interacting with each other. This is not a mixture, or sorry, this is not a solution, because it's not one phase. It's not been put together into one thing. This is still two things, so that's not a solution, right? Solutions have to be one phase. They have to look homogeneous and uniform. So again, solute, the thing dissolved, solvent, the thing doing the dissolving. A solution is when the solute is dissolved in the solvent. Just a picture to help you see that. Not wanting to advance. This is awesome. I love my computer right now. There you go. Phases. We talk about phases of matter, states of matter, okay? And in a solution, certain phases can dissolve other phases of matter. You can have other things be the solvent other than a liquid, but most of the time, a liquid is the solvent. Most solutions are fluid solutions, and so a liquid can dissolve other liquids or solids or gases. So an example of liquid dissolving another liquid would be like if you were to make your own at-home soda, and you start with water and simple syrup, like corn syrup or caro syrup, and you take this liquid, this syrup, and you whisk it into some boiling water, and it dissolves. And now you have one liquid dissolved in another liquid. You have sweet water. Okay? You go from there to make it a soda. That would be a liquid dissolving a liquid. A liquid dissolving a solid, we've talked about salt water. That would be an example of that. Salt is a solid. You put it in water, it dissociates, it dissolves. That's a liquid dissolving a solid. You can have liquids dissolving gases. If you are at home, again, making your own soda, and you get your sweet water, and then you add whatever flavoring you want to it. Let's say you want to make black cherry soda. So you've got your sweet water, and then you have some black cherry extract that you drip in there. And now it's purple, sweet, cherry flavored water, but it's still flat. Now you take your soda and you inject carbon dioxide into it. And most of the time when people make their own soda at home, they get some dry ice, crush it up into little pieces, and whisk it in. And the dry ice will turn into gas, and so it'll carbonate your soda, and it'll also chill your soda. Now you've got homemade black cherry soda. And what you just did is take a liquid and dissolve some other liquid and some other gases into that, and now you have homemade black cherry soda. And that is an example of a liquid dissolving another thing. Liquids that can form a solution with another liquid are said to be miscible. Miscible means they are able to dissolve one another. So sugar water, simple syrup like corn syrup, is miscible with tap water or pure water because sugar is polar and tap water is polar, and so they can dissolve one another. Alcohol, drinking alcohol, is polar and water is polar, and so you can dissolve drinking alcohol in water, and you get various kinds of liqueur or liquor from having done that, and that's miscible. They dissolve. Something that can't dissolve something else, like oil in water, you mix those two together, whisk them up, and watch them, and they don't stay mixed. They separate. The word for that is immiscible. Most of the time, miscibility, can it be mixed or can it not be mixed, has to do with the two of them being similarly polar. And that's the point of the lab we're going to do later this week, is looking at what can or can't dissolve something else. Okay? So most of the time, miscibility has to do with their polar natures. Love my computer today. Come on. Oh my gosh. Let me go stand closer to you. There you go. Whoops, wrong direction. Boy, I love my computer today. There you are. Okay, so soda is a mixture of solids in liquid and liquids in liquid and gases in liquid. It's a great example of a solution. And when it settles out, it looks like one thing. Okay? This is immiscible. Oil and water, as we've already said, are immiscible. They cannot be mixed. Okay? Solid solvents can also dissolve liquids, other solids, and gases. Most of the time, a solid dissolves another solid. And the example of that would be a metal alloy, where you have, let's say you're you're an old ancient soldier, and you want to make a shield for yourself to protect yourself in battle. This is before we've discovered iron and steel, but we do have copper, and we do have aluminum. And the bummer is that both of those metals, copper and aluminum, are really soft. So it's a bad thing to make a shield out of, because somebody swinging a big, heavy mace at you is going to go right through your shield. It's made out of aluminum or copper. But kind of spooky, if you melt the copper and melt the aluminum and make a mixture of molten copper and molten aluminum, you get a relatively strong substance called bronze. And bronze, you can make a shield out of bronze. Bronze is going to be strong enough to keep you safe. So that's a solid dissolving a solid. Now, in that example, you have to melt them both so they're kind of liquid before you put them together. But you can make a solid dissolve solid in their solid state as well. Sometimes you can take a solid and another solid and crush them up together in a mortar and pestle, and one will dissolve the other, and they didn't turn into liquid. So solids can dissolve other things. You can have gases dissolved in solids, you can have liquids dissolved in solids, and you can have solids dissolved in solids. Okay? The only one that can't dissolve all three phases of matter is a gaseous solvent. Right now you are breathing room air, normal atmospheric air. We haven't stuck anything strange in the air in this room. But in this gaseous mixture that you're breathing, it's mostly what? Does anybody know?
Oxygen.
No.
Nitrogen.
It's mostly nitrogen. Yes. About 75% or so of what you're breathing right now is nitrogen. And then, but it's not all nitrogen, because then you would be dead. Your body requires another gas to be in there, oxygen, right? That's what you require to do your metabolic activities. So there is oxygen dissolved in the nitrogen. There's also carbon dioxide dissolved in the nitrogen, because I'm talking and you're breathing and nobody's holding their breath for this entire class. So we're putting out carbon dioxide. The carbon dioxide is dissolved in the nitrogen. The nitrogen is also dissolving the oxygen. So that's a solution. If you look in the air, you don't see layers of it. You're not like, oh, there's the nitrogen, and here's some oxygen, and there's some carbon dioxide. You don't see layers. It is one phase. It is dissolved, homogeneous. But the solvent is nitrogen, and the solutes are oxygen and carbon dioxide and some other trace gases as well. So you can have gaseous solvents, but they can only dissolve gaseous solutes. It would be kind of strange to have a gaseous solvent and a solid solid and be like, oh, there's a chunk of something. That would be weird. And so gases can only dissolve other gases. And here we have concrete. Concrete flooring is an example of a solid that has dissolved other solids. And it needed to be in a liquid state at first, but then the liquid leaves and you have a solid dissolving other solids. And that's what concrete is. Okay. Brass, again, is an alloy of copper. Steel is an alloy of iron and some other elements. Here's a cloud, which is a gaseous form of water, and that gaseous form of water is dissolved in the atmosphere, nitrogen mostly, and other gases. So again, this is a mixture of gases and gases. Solvation. Now, solvation is different from salvation, right? Yes. Solvation is the process in which a solid solute moves into a liquid solvent. So adding sugar or salt to water to make either syrup or salt water, that is the process of solvation. Salvation requires the Word of God and the Holy Spirit and faith. Solvation just requires water and solute. A little different. However, after you experience salvation, you should be baptized. And if we put you in the water and you cease to exist, that would be solvation after your salvation. But hopefully you come back out of the water and are dissolved. Yeah, so many puns. Solvation, thank you. The process in which a solid solute moves into a liquid. I guess even if you as a whole came out of the water after you're baptized, I'm sure some dirt on your skin stayed in the water. So maybe there is salvation after salvation after all. Solvation is basically two steps. Dissociation and ionization. Two steps. Dissociation, the solute particles need to separate from each other. So if I have a lump of sugar and I want to sweeten my tea, the tea is the solute and the sugar is the solvent. When I drop the lump, when I drop the sugar, into the T, the first thing that happens is all of the sugar molecules need to separate from each other. And so they are held onto each other by intermolecular forces in a solid crystal. And then they get into the water, and the water provides some increased thermal energy, so they start to shake a little bit, and they shake away from each other. And now I have dissociated my sugar molecules, and they're floating around in the water. That's dissociation. But they need to ionize with the solution. After they are just by themselves, now they're going to give or exchange some electrons with the solutes, so that the solutes polarity and the solvents polarity can attract each other and cause it to be really, really happy in solution. This is where miscibility comes in. If something can't ionize in the solution properly, then it doesn't dissolve, and you wind up with a layer of something at the bottom and a layer of something at the top, right? So 2 steps to solvation. Dissociation, break it up into molecules. Ionization, pass some electrons back and forth so that there are charges there. And then those charges help everything to be attracted to itself and to dissolve in solution. Solvation, dissociation, ionization. So here's an example of that. This is salt water, right? Water has a polar portion. It's partial positive and a partial negative. And this salt is chlorine and sodium. And so the positive parts are going to be attracted to the negative parts of water. And the negative parts are going to be attracted to the positive parts of water. So first this is going to break up into smaller pieces through dissociation. And then in ionization, the polar portions of the solvent will be attracted to the polar portions of the solute. And we have ionization going on here. And that's why salt likes to hang out in water. It's quite happy. The dipole-dipole interactions work. Okay? Solvation is generally exothermic. Most of the time, it releases more energy than it absorbs because there is a higher degree of chaos and a lower degree of order in a chunk of something broken up into little bitsy bits floating around in water than there is in it organized in a crystal. So when a solid is dry and organized in a crystal, there's more order, there's more chaos in a solution. Things tend to favor chaos. Generally speaking, chaos is a lower energy state than order. So dissolving something in solution releases more energy than it absorbs. Sometimes you have to give it a little bit of energy to get it started. You have to maybe heat the water for the sugar to start to dissolve. But once that process has begun, it will continue on its own heat that it's releasing, on its own energy that it's releasing. We can measure the amount of energy change in a solution as it is being formed, and we could call that the enthalpy of solution. Enthalpy, remember, is a word you've seen before that has to do with the amount of energy change, usually heat change, okay, in a reaction. And here we're not talking about a chemical reaction, here we're talking about something being dissolved. So it's not the enthalpy of reaction, it's the enthalpy of solution. The amount of change of energy that making a solution gives off, okay? And so generally speaking, if you were to very carefully measure the temperature of a solvent and then dissolve something in it and then measure its temperature very carefully afterwards, you find the temperature rises ever so slightly. Tap water, take its temperature, pour some sugar in, stir it up, wait till it's all the way dissolved, take its temperature again, slightly warmer. Not a lot, but a little bit. And that slight increase in temperature is because of the release of energy of the sugar going into solution. Okay, enthalpy of solution. And as I said before, typically light dissolves light. Non-polar things dissolve non-polar things. Polar things dissolve polar things. And that we'll play with that lab on Thursday and Friday. Okay, this just shows energy of an energy diagram of solvation of something going into solution. the pure components will have a certain amount of energy. And then you have to add energy to separate the solvent molecules. You have to add energy to separate the solute molecules. And then once they go into solution and they ionize, they release energy back. If it just lands at the same energy level that it was before, then no energy has been gained or lost. If it doesn't release as much energy as it took to make it, then that's endothermic. That's very rare. Most of the time, when you form a solution, it releases more energy than it absorbed, and so it's an exothermic process, right? We've released more energy. Help, help, I'm dissolving, says the polar bear. The grizzly bear says, but bears are insoluble. And the polar bear says, that's easy for you to say, you're not polar. Oh, man. I can barely contain myself with that joke.
Oh my goodness.
Okay. Okay. Solutes tend to dissolve faster at higher temperatures and pressures. And so you tend to be able to dissolve salt in hot water faster than you can dissolve salt in cold water. And because the more energy that's in the solution, the more energy that can be added to the solute and to the solvent to separate the molecules a little bit and create room for the solute to move into the solvent. So typically, solutions are made faster at higher temperatures. And then we have to describe some words here. The mass of solute divided by the mass of a solution. If I want to know how much of something is there, how rich is this solution? How concentrated is this solution? I could weigh my solute, and I could weigh my solution, and I could then put them together, and I would know that I have a certain percent mass solution. Okay? Then I could also go about it another way. I could look at the percent volume, and I could say how much volume of solute did I put in how much volume of solution. And both of these are good ways of talking about how rich a solution is. A 20% salt solution by mass would mean that if I had 100 grams of solution, initially that was 20 grams of salt. And 20 grams of salt, and then the resulting thing is 20 grams of 100 grams of solution. I have a 20% by mass. Okay? Or I could do it the other way around. I could say I have 4 milliliters of simple syrup, and then after I make my solution, I have 100 milliliters of solution. I have then a 4% by volume sugar water or simple syrup water. Okay? So percent volume or percent mass. Now, pay attention. I put this in bold because you'll see another thing on the next slide. That's mass of solute, and then not mass of solution, but mass of solvent. So just notice that this, when you're talking about percent mass, it's mass solution. Just keep that straight. Okay. Percent mass is mass of solute over mass of solution. Percent volume is volume of solute over volume of solution. These are ways of talking about how rich or dense a solution is. Then the other two ways of doing that is molarity and molality. Molarity is how many moles of solute do I have per liter of solution. Moles of solute per liter of solution. So this is the most common. Molarity is the most common way of measuring how concentrated the solution is, especially if you're talking about acids. Sometimes in labs, you'll see that it calls for 4 molar hydrochloric acid. And what that means is that in every liter of solution, there should be 4 moles of hydrochloric acid. And then you'd have to know the molar mass and do some stoic and figure out how many grams of that is. But moles of solute per liter of solution, this is the most common way of measuring the density of solution. Molality is a little bit different. Moles of solute per kilogram of solvent. Moles of solute per kilogram of solvent. And that's the one that gets confused sometimes with percent mass. So here I have moles of solute. So again, I could have 4 moles of hydrochloric acid dry hydrochloric acid. And then I combine it with 1 kilogram of water, and I would have a 4 molal solution, 4 molal instead of 4 molar. Okay. The difference is, are you weighing the solution, or are you determining the volume of the solution at the end? Molarity and molality. Okay. I think I have some examples here to show you the math. Yes, I do. Alrighty. If you dissolved 5 grams of solute in enough solvent so that the entire solution had a mass of 1 kilogram, what is the percent comp by mass? Okay, so that's pretty simple. I need everything in kilograms first. So 5 grams is 0.005 kilograms. So that would be 0.5% composition by mass. 0.005 divided by 1 is 0.005, and then you have to turn that into percentage, right? So that'd be 0.5% composition by mass. Here's another one. If you dissolved 10 mils of solute in enough solvent so the entire solution had a volume of 4 liters, what's the percent comp by volume? And again, you need it all in liters. So 10 milliliters, we have to convert that to liters first. That would be 0.01 liters. And then the whole solution is 4 liters. 0.01 divided by 4 is 0.0025. So that's 0.25% composition by volume. Okay, it's just simple division. None of these are very hard. Let's look at another one. If you dissolved 3 moles of solute and enough solvent to create 2 liters of solution, what would the molarity of that solution be? So 3 moles and 2 liters. 3 moles divided by 2 liters is 1.5 molar. And the last one. If you dissolve 6 moles of solute in 8 kilograms of solvent, what would the molality of solution be? Okay? And again, this is not kilograms of solution, this is kilograms of solvent. 6 moles of solute, 8 kilograms solvent. Ooh, I said solution. So that would be 6 divided by 8 is 0.75 molal. Okay? Let's do this one together. 5 grams of sodium chloride dissolved in enough water to make 500 milliliters of solution. What's the molarity? Well, I didn't give you moles. I gave you grams. How do I get from grams to moles? How do we get from grams to moles? Blow the dust off stoichiometry chapter. Yeah. How do we get from grams to moles?
You multiply by
That's
2, right?
last
You
That's
multiply
so
by
last
2,
semester.
right?
Multiply by
You divide by the molar mass. Thank
Just
you.
kidding.
Okay, divide by the molar mass. So I have 5 grams. I need to first figure out how many moles are in 5 grams of sodium chloride. Sodium is 22.99 grams per mole. Chlorine is 35.45 grams per mole. So add those up, 58.44 grams per mole. I have 5 grams. I'm going to wind up dividing by 58.44. So I have 0.085558 moles of solute. Now I need to figure out my molarity. So I have that many moles of solute divided by that many liters of solution. So I do the division. I wind up with 0.171116 molar, significant digits. I have 2 and 3. There's a decimal point there. So I need 2. So 0.17 molar is my answer. Okay? Sometimes you will need to remember your stoic for this chapter, but actually you'll need to remember your stoic for the rest of your life. So that's okay. I think that's it. Any questions? We got started a little late, but we still made it, so that's good. Okay, thank you. Take your cover sheets out. I'll come around and stamp you for your behavior today. Thank you very much.